Welcome to the first module of the massive online open course, Geoscience, the Earth and its Resources. This is the first step of a long journey which will provide you a more profound understanding of how the Earth works. Eventually, this will enable you to predict the nature of the subsurface of the Earth. You will also learn to use the Earth's resources in an efficient and responsible manner. The journey of this MOOC is organized in 5 main steps. A general acquaintance of the Earth, horizontal and vertical movements which lead to the formation of mountains and sedimentary basins, how sediments are produced and then transported to the sea, and how different types of sediments are deposited in the marine environment. The last 2 components of the MOOC are dedicated to 2 of the most important commodities relevant to geological studies: hydrocarbon and water. The Delft engineers want to understand, but also to use their knowledge. Like most journeys, your time and energy are limited, so we will focus on subjects of primary importance. This course is only the beginning of your geological life, and you will have plenty of opportunities to deepen your knowledge in the future, in Delft or elsewhere. Here you see the rock cycle. You see clouds and rain erode the mountains, producing sediments, which are then transported to the sea. At subduction zones, sediments and other rocks are brought at depths of tens of kilometers and metamorphosed. Some might even melt, forming magma and magmatic rocks. Others come back to the surface. 3 types of rocks are defined: magmatic, metamorphic, and sedimentary rocks. We will start our journey with magmatic rocks, which form from the consolidation of magma at depth or at the surface of the Earth. These 2 types of rocks are very different and are named intrusive and extrusive. You will see more of this in the coming slides. Where does the magma come from? The answer to this question is not obvious, as practically all rocks of the outer 3,000 kilometers of the Earth are solid. Where does then the magma come from? How is this generated? We will need a bit of physics and chemistry for this part of the journey. In this diagram you see 2 curves. The geothermal gradient indicates temperatures found at different depths in the Earth. The dashed curve shows the temperatures at which typical mantle rocks melt. As you can see, temperatures are lower than melting temperatures, which means the rocks are solid and no magma is generated. Now, how can we bring then a rock to melt? The first process is simply heating. We call this creating a thermal anomaly. This is feasible, but physically very difficult in the deep Earth. A second possibility is to move the rocks upward. This is potentially a good mechanism, but movements of many kilometers are needed. The third process relates to the change of position of the melting curve. When fluids are added to the system, the melting curve shifts to the left and rocks previously in the stable field starts melting. This is what happens in subduction zones, where fluids are added to the crust, thereby lowering the melting temperature. During progressive melting, a very important process takes place, which is called fractionation. As a result, the magma generated by a rock can be chemically very different from the parent rock. This is caused by the fact that the rock is typically composed of different minerals with different melting temperatures. With increasing temperatures, the first minerals to melt are those with a low melting temperature. The resulting magmas will have a percentage of silica SiO2 much higher than the original rock. With increasing temperature, a larger portion of the rock will melt and the composition of the magma will approach that of the parent rock. As a result of fractionation, limited melting produces magmas which are acid and relatively cold, 600–700 degrees. Magmas generated by complete melting, on the contrary, are more basic and have generally higher temperatures. The magma has a density lower than that of the surrounding rock and will start moving upward driven by the negative density difference. We call this buoyancy. A simplistic but interesting quantity description is provided by Stokes' law. This shows that the velocity of the rising magma bubble is directly proportional to the density difference and inversely proportional to the viscosity. Driven by its lower density, the magma will begin moving upward. Magmas, which are relatively cold, have a high viscosity, will move slowly and are likely to remain trapped somewhere in their path towards the surface. They will consolidate and an intrusive rock is formed. Intrusive rocks are typically coarse-grained, and you can see in thin section that the entire rock is built of fully developed crystals. Intrusive rocks are of great importance. They provide the heat driving most geothermal fields and emit fluids which generate major ore deposits worldwide. Hot magmas have low densities and very low viscosities and are likely to reach the surface of the Earth, creating volcanoes, one of the most fascinating phenomena in nature. Volcanoes show very different characteristics and behavior depending on the magma. High-temperature magmas produce large but flat edifices. The lava flows gently and regularly out of the crater. Low-temperature magmas, on the contrary, form steep and more irregular complexes and are much more dangerous, with frequent explosive activity. In this last slide, you find a scheme for the classification of magmatic rocks. In a plot showing the percentage of silica SiO2 versus various types of minerals, you can see that different domains correspond to different types of rocks. And as you can see, two different names exist for each composition, one for intrusive and one for extrusive rocks. We have now looked at magmatic rocks, and now you are ready to tackle the second type of rocks, namely metamorphic rocks. Welcome! This is the rock cycle, a scheme we have already presented in previous clip. After having looked at magmatic rocks, we will focus now on metamorphic rocks. When a rock, whatever its origin, is exposed to high temperatures and pressures, it will be profoundly modified. A metamorphic rock is born. Do you want to see what metamorphic rocks look like? Take your backpack and go up into the mountains. There you might find rocks which have been formed at depths of 10 or 20 kilometers and have come all the way up for you to collect. These rocks will be very different from the magmatic rocks we have seen in the previous clip, and from the sedimentary rocks you will see in the next one. When tectonic plates converge towards each other, a large region of deformation occurs, where rocks are squeezed and deformed, typically at high temperatures. These temperatures can be of several hundred degrees, and pressures in excess of 3 or 4 megapascal, which corresponds to the weight of a column of several kilometers of rocks. With higher temperatures, old minerals become unstable and new ones will form, providing very different aspects to the rock. When deformed at high pressures, the rock will develop a strong planar fabric and again will look very different. Changes of temperature with depth are described by geothermal gradients. We define a gradient characterized by high temperatures and low pressure, contact metamorphism at the figure. We define a regional one with intermediate values called regional metamorphism, and one with very low temperatures even at high depths, named blue schists. Different types of metamorphic rocks form under these different gradients. Regional metamorphism is found in the areas where two lithospheric plates collide with each other, there where mountains form. This is the most common form of metamorphism. A sand or a shale brought at higher depths will first become a green schist, will then acquire coarser size and eventually become igneous. At higher temperatures, it might even start melting, creating migmatites. Gradients in subduction zones are characterized at much higher pressures and result in very special rocks, blue schists, Famous examples are found in the Alps, in Japan, and in many other mountain belts. In these settings, rocks reach depths of several tens of kilometers and then, even more strangely, are brought back to the surface. On the opposite side, we find gradients characterized by very high temperatures at shallow depths. This is the case, for instance, of rocks surrounding a magma chamber. The rocks will be warmed up and cooked with little deformation and a lot of fluid interactions. Intense deformation at high pressures and temperatures is often coupled with circulation of hot fluids. These are key for the formation of ore minerals. We have followed rocks down to large depths where they have been modified and metamorphosed. Some rocks will start moving upward, thereby uplifting the surface of the Earth and creating mountains. These are the source of some of the most important types of sedimentary rocks. The third type of rock forming the outer part of the Earth, which we will look at in the next clip. Welcome again. In this clip, we will focus on sedimentary rocks. Movements in the Earth have created mountains. Erosion will start, and mountains will produce sediments, which we call terrigenous sediments. This is the source of our sedimentary system. The sediments will be transported by torrents through the mountains, will reach large open valleys, and will eventually enter the sea where they will accumulate. This is the source-to-sink system, a key concept to understand sedimentary rocks and the resources they contain. Sedimentary rocks are crucially important for society and therefore for this course. The largest cities on Earth are on sedimentary rocks. Mankind as a whole depends on the responsible use of the subsurface. Water for agriculture and drinking, geothermal energy, an increasing number of subsurface infrastructures, hydrocarbons, mining and storage of CO2 are all examples of the increasing use we make of the subsurface. The source-to-sink system works somewhat like the economy. The source is comparable to the factory where the goods are produced. These are the sediments in our case. The sediments are then transported by different means and eventually will reach the market, which in our sedimentary system is called the sink. Let us look first at how sediments are produced. Expanding and contracting ice, rain, and wind are all major agents breaking mountain rocks and producing sediments. In addition, rainwater, often acid, chemically attacks less stable minerals such as feldspars, producing clay minerals. Vertical movements in the source area are of great importance in sedimentary system. If the source area experiences strong vertical movements, relief is rejuvenated, and sediment production can continue for a long time. If, on the contrary, if vertical movements decrease or even end, then the source area will become less productive, eventually producing no sediments at all. Vertical movements, rock types, and climates in the source area are the key factors controlling the amount and type of sediments produced. Eroded sediments are taken over by water or wind and transported to the sea. In the mountains, they will be carried by irregularly flowing torrents and creeks. In the foothills and in the wide, gentle plains, rivers will be wider, often meandering, and will irregularly flood the surrounding plains. Eventually, the rivers will reach the sea, often forming large deltas and delivering the sediments to the final sink, the marine domain. A key concept in the analysis of sedimentary succession is that of accommodation space, which is the vertical dimension of the space where sediments can be deposited and preserved. In the marine case, this corresponds to the height of the water column between the sea level and the sea floor. In the case shown in the picture, the accommodation space could be around 10 meters. If nothing else changes, sediments delivered to the sea will gradually fill up the accommodation space and the maximum sediment thickness will be comparable to that of the accommodation space, that is 10 meters. In the slide, the remaining accommodation space is 4 meters. However, sedimentary successions in the world can be kilometers thick. We are clearly missing something important. The existence of a thick sedimentary succession roughly deposited at the same water depth requires an increase of the accommodation space through time. This is achieved by letting the lower boundary of the accommodation zone descend through time. The downward movement of the surface of the Earth, which is called subsidence, is a process of key importance in geology and in our MOOC. Sediments eroded from the mountain are not only the only type of sediments you will find in the sea. Away from deltas and in areas where the waters are clean, carbonate sediments can develop. These are sediments created by organisms and therefore are necessarily linked to life. This is the domain of coral reefs, or large mud flats covered by algae, and of the clean white sands of shells and biological grains.